Hello everyone, this is our work, second-order graph ODEs for multi-agent trajectory forecasting. Multi-agent trajectory forecasting is a challenging problem because agent interactions and underlying agent temporal dynamics jointly affect each agent in a nonlinear and complex way. Previous methods use graphs, social pooling, or spatial transformers to model the agent interaction, while they apply RNNs or temporal transformers or first-order ODEs to encode the underlying agent temporal dynamics. However, there are two limitations. First, previous methods overlook how agent interactions evolve with distance and velocity information among agents. For example, as shown in the figure, there are several cases. When two agents are far away from each other, their interaction should be weak. On the other hand, when they are close to each other but are moving in opposite directions, they may not affect each other. Second, they do not adequately fit the physical motion law. According to Newton's second law, the force, which is regarded as agent interactions in our approach, affects acceleration, while first-order ODEs only consider the distance information which affects velocity. These modeling limitations often lead to inaccurate results, such as reduced forecasting accuracy and collisions among agents. To overcome the limitations, we propose the Agent Graph ODE. It is a novel approach that models both agent interactions and continuous second-order temporal dynamics explicitly. In detail, we first incorporate distance and velocity information to model agent interactions by constructing dynamic interaction graphs in real-world space. Secondly, we model continuous temporal dynamics using second-order ODEs. We use second-order ODEs where the second-order derivative of the latent state is influenced by agent interactions. Thirdly, we do extensive experimental study to show that our method achieves improved accuracy on complex trajectory forecasting. Our method is an encoder-decoder architecture. It consists of three components. Firstly, we use position and velocity information in real-world space to construct dynamic interaction graphs. The interaction graphs are used in the encoder and decoder to extract agent interaction features. Secondly, we use the spatial-temporal transformers as our encoder to transform the real-world trajectories into latent space, which are used for computing initial values for ODEs. Lastly, the decoder module includes two parts. One is building and solving ODEs in the latent space, and the other is recovering real-world trajectories from the latent space trajectories. We will introduce these three components in detail. We use distance and velocity information to construct interaction graphs. The interaction graphs are constructed based on the equation. The p is the position in real-world space and u is the velocity in real-world space. The function means that two agents will not affect each other if they move away from each other. Otherwise, if they are moving towards each other, then agent I and agent j are connected. We use the spatial-temporal transformer as our encoder. The spatial transformer and temporal transformer are concatenated to generate latent vectors. Different from the standard attention module, we incorporate interaction graphs in spatial transformers to model agent interactions more explicitly. The Mij denotes the ratio of relative velocity, in the direction along agent I and j, to the respective distance. We add the relative velocity to the attention mechanism. It means that the attention should be large if the relative velocity of moving together is large or the distance is small. After computing the latent vectors with the encode, the decoder builds and solves the ODEs to obtain future latent trajectories. H is the latent state for each agent and v is the latent velocity. The evolution of latent state H is modeled by our second-order ODE. The first equation is the first order, which means the derivative of position is velocity. The second equation is the second order. It means the derivative of velocity is acceleration, which is affected by agent interactions. The agent interactions include distance information, interaction intensity and interaction graph edge. These equations are inspired by Newton's second law. We also compute the initial values for the ODEs using these three equations. Then we can solve the second-order ODE to forecast the future trajectories. We conduct experiments on IND, round, high-D traffic datasets and NBA SportView dataset. We compare our method with previous methods. The traffic datasets record vehicle trajectories at German highway by drones. The NBA dataset consists of player and ball trajectories. We use average displacement error as the evaluation metric. The table shows that FF forecasting is for a long period of time. Our method always performs best in curved trajectories, which means our method can deal better with complicated trajectories. Our method achieves best performance on NBA dataset. It verifies the capability of our model to handle more complex scenarios because sports agents exhibit more frequent changes. We also conduct experiments to show how the agent's trajectory is modified when a sudden obstacle appears. To model the sudden obstacle, we place a static in the trajectory. The table shows that our method achieves the lowest collision rate while avoiding the static agent. These three figures visualize how our method makes the agent avoid the obstacle. The blue trajectory is the inputting and the white one is the predicted result. The black point is the sudden obstacle. The results show that the agent of our method can avoid the obstacle and others fail. In conclusion, we propose Agent Graph ODE to utilize second-order ODEs to model temporal dynamics, which adhere to Newton's second law. Our experiments on traffic trajectory and sports datasets demonstrate our method outperforms other methods in terms of forecasting accuracy, particularly in complex environments. Additionally, it exhibits superior capability in effectively handling sudden situations. This concludes our presentation. Thank you.